On to the second part about differentiation, where we're talking about tangents and their normals. So we know now what tangents are. What exactly are normals? Well, the line that is perpendicular to that tangent or to the curve at that point, that perpendicular line that crosses that point as well, the point at which the tangent exists, that is what's called the normal. So it's basically perpendicular to the tangent at the point where the tangent exists. Well, if the value of dy over dx, which is the gradient of the tangent, at a point A, which is denoted by the coordinates x1 and y1, is m. So that's the gradient at the point x1, y1. The equation of the tangent is going to be this right here. Y minus y1 equals to m x minus x1. That is one of the ways that we did equations in the topic of coordinate geometry. But if you are not familiar with this, then the other way, we will just have y equals to mx plus c, where c is the y-intercept. Okay? If that's the case with the tangent, then the equation of the normal from this method will be the exact same, just that the gradient will now be negative 1 over m. So the reciprocal of the original gradient times negative 1. So if the original gradient was negative 2, then we make it a reciprocal 1 over negative 2, then we multiply by negative 1. We get 1 over 2. So if this was the gradient of the tangent, then this would be the gradient of the normal at that point. As for the other method of showing an equation of a line, what we will now do is just change the value of m from m to negative 1 over m. So y equals to negative 1 over mx plus c, and you will have to find a new y-intercept where you can plot in these points that it is a normal at. Let's do some examples. Firstly, find the equation of the tangent and the normal to the curve y equals to 2x squared plus 8 over x squared minus 9 at the point where x is negative 2. So firstly, what we will have to do is find the gradient of the tangent so that we can use that to find the gradient of the normal line. So for that, we'll need to differentiate this. That will be dy over dx equals to 4x minus 16 over x cubed. And to find the gradient at the specific point where x equals to 2, just substitute that in. We get 4 times 2 minus 16 over 2 power 3. This gives us 8 minus 16 over 8, which is just 8 minus 2, which is going to be 6. So that's the gradient of the tangent at the point where x is equal to 2. Then the gradient of the normal line will be the reciprocal of the gradient of the tangent times negative 1. So 1 over 6 times negative 1, which is going to be negative 1 over 6. So at the moment we have y equals to negative 1 over 6x plus c for the equation of the normal. To get our value of c, what we can do is put in the value of x 2, and we need the value of y at that point where x equals to 2. And to find that, we can just go and put the 2 into the original equation. So we have y equals to 2 times 2 squared plus 8 over 2 squared minus 9. That's going to give us 8 plus 2 minus 9, which is going to give us 1. So our y value is going to be 1 at the point where x is equal to 2. Then what we can do is substitute that into the equation. We get 1 equals to negative 1 over 6 times 2 plus c. Rewriting this will give us that c is equal to 4 over 3. Therefore, our equation of the normal line will be y equals to negative 1 over 6x plus 4 over 3. Multiplying out by 6 on both sides to get rid of the denominator will give us 6y is equal to negative x plus 8. That's going to be our equation of the normal. For the tangent, we have y equals to 6x plus c, where we can put in those same coordinates 2 and 1 to get 1 equals to 6 times 2 plus c, which gives us that c equals to negative 11. Therefore, our equation of the tangent will be y equals to 6x minus 11. For the second example, the curve has an equation y equals to 4 minus root x power 3, and the normal at the point P and the normal at the point Q intersect at a point R. So what you want to do is find the equation of these two normals, then substitute them with each other because they intersect, and the coordinates that you get from that is the point R. Firstly, what we need is the gradient of the tangent so that we can use that to find the gradient of the normal line. Therefore, what we will do is derive this equation right here. Therefore, dy over dx is equal to the gradient of whatever is equal to the derivative of whatever is inside the bracket, which is just 4 minus x power a half. And the derivative of this is going to be negative 1 over 2 root x. Then you will multiply by the power, so times 3. Then multiply by the bracket, power, and minus 1, so 3 minus 1. So minus root x power 3 minus 1, which is 2. So our derivative is going to be negative 3, 4 minus root x squared over 2 root x. Then you want to find the gradient of the tangent at point P and point Q. At point P, that means when x is equal to 4, our gradient is going to be negative 3, and therefore the gradient of the normal is going to be the reciprocal of this times negative 1, which is equal to 1 over 3. That's going to be the gradient of the normal. On the other hand, when x is equal to 9, our gradient of the tangent is going to be negative 1 over 2. Therefore, the gradient of the normal is going to be reciprocal of this times negative 1, which is going to be positive 2. With that, we get two equations. This time I'm going to use the other format. Y minus y1 equals to mx minus x1. We want to find the equation of the normal line. Therefore, we're going to use the coordinates and the gradient of the normal line. At P, our y1 and x1 was going to be 8 and 4 respectively. So y minus 8 is equal to the gradient at P is 1 over 3. So 1 over 3 times x minus 4. On the other hand, for Q, we have that y minus 1 is equal to the gradient of the normal at Q is 2 times x minus 9. This will give us two equations for the two normals. The first one being 3y is equal to x plus 20. On the other hand, this equation is going to be y is equal to 2x minus 17. Now we have the equation of both the normals, and what's happening is that they have intersected at the point R. Therefore, the y values are the same and the x values are the same. So what we will do here is simultaneous equations where we will solve it. And when you simultaneously solve this, you get that x is equal to 14.2 and y is equal to 11.4. And so these are going to be the coordinates of point R. So R will be 14.2 and 11.4. Something else we have is second derivatives. If we differentiate y with respect to x the first time, we get dy over dx, and that is used to calculate the gradient. On the other hand, when we differentiate this again with respect to x, obviously, we will get the derivative of that thing, and that is written like this: d square y over dx squared. And this is the second derivative of y with respect to x. So if we had an equation y equals to x cubed plus 5x squared minus 3x plus 2, our first derivative we know is this is going to become 3x squared, this is going to become 10x, and this is going to become negative 3. This is going to be 0, so it's not going to be there. So we're going to get 3x squared plus 10x minus 3. Then you take the derivative of that again with respect to x, and we will get 6x from here plus 10 from here, negative 3 will just become 0. Therefore, our second derivative of this original equation will be 6x plus 10. Obviously, that can apply to functions as well, where instead of you writing f with one line and x, this is the first derivative of the function f of x, you will write f with two lines and x. So this is the second derivative of f. That's how it's written. So let's do an example. Given 5 over 2x minus 3 cubed, find the second derivative. So 5 over 2x minus 3 cubed is just 5 times 2x minus 3 power negative 3. And to find the first derivative of this, you take whatever's inside the bracket, take the derivative of that, multiply outside. So 5 times the derivative of whatever's inside is just going to be 2. Then you multiply by the power as well, so times -3. Then you write the bracket as it is, 2x minus 3, then subtract 1 from the power, which will become -4. So this will end up becoming -30, 2x minus 3 power -4. That's the first derivative. For the second derivative, I will have to differentiate this again. So we'll do that again. So -30 multiplied by the derivative of whatever is inside the bracket, which is again 2. Then you multiply by the power, so times -4. Then multiply by the bracket, 2x minus 3, and the power subtracts 1, so -5. Therefore, this ends up becoming 30 times 2, which is 60, times 4, which is 240. So 240, 2x minus 3 power -5, which is just 240 over 2x minus 3 power 5. And that is going to be our second derivative, d2y over dx squared. Final example, a curve has an equation y equals to x cubed plus 3x squared minus 9x plus 2. Find the range of values of x for which the first derivative and the second derivative are negative. So we'll start off with that. We can find the first derivative and the second derivative first. So first derivative for this is going to be 3x squared plus 6x minus 9. That's your first derivative, dy over dx. Then our second derivative, d2y over dx squared, is going to be the derivative of this right here, which is going to be 6x plus 6. And when are these values negative? So when are they going to be less than 0 for both of them? The second derivative is easier to calculate, where 6x plus 6 is less than 0. Therefore, 6x is less than -6. Divide by 6 on both sides, we get that x is less than -1. On the other hand, this one right here, the way we do it is, we draw the way the curve would look like. We draw our 0 line, yes? Then we find the two intersection points when this equation is equal to 0. And that's going to be 1 and -3. Then we want it to be less than 0. So we are looking at this range here, where it is below that 0 line. So when x is between 1 and -3 is when our d squared y over dx squared is negative. So what we have are two ranges. One of them is between -3 and 1 not inclusive, and the other one is less than -1, again not inclusive. On a number line, just to show, this is going to be -3, this is going to be 1, and let's say this is -1. The one for the second derivative is going to be from here, not inclusive obviously, so we draw an open circle towards the left. While for the first derivative, it's going to be from 1 up to -3, open circle on both ends. Combining both of them, for when both of them are negative, we will see that the endpoint for the dy over dx and the endpoint for the second derivative, we will get that the range is going to be from -3 up to -1. This range of values is when dy over dx and the second derivative, d2y over dx squared, are both going to be negative, this range right here. Part B tells us to show that the second derivative is not equal to the first derivative squared, which people might confuse with the way it looks at first. This looks like it's just dy over dx squared. So for that, we're going to prove that. So 6x plus 6, is that going to be equal to 3x squared plus 6x minus 9 squared? And we see obviously not, because on the left side we're going to have 6x plus 6. Our first term in itself will be 9x power 4, which obviously is nowhere on the left side. Therefore, the right side is not going to be equal to the left side. And so, the second derivative is not equal to the first derivative squared.